So these sessions, which I run every month via Makespace here in Cambridge, are really about me sharing some of my engineering, electronics, some electronics engineer, just sharing some of my background and experience. I've been doing this stuff for 30 years as an electronics engineer, and I never stop learning. In fact, in writing today's presentation, I've learned something new, which I will show you all. A brand new elephant trap I've discovered. So today's going to be all about proximity, and we're going to be using the Raspberry Pi Pico. In fact, why don't I just try to share camera just to give you a quick image of what we've got. So if I do share, there you go. Hopefully you can all see that. So this is our setup that we've got today. We'll have a look at this in a minute on slide, but we've got this is a digital infrared sensor, and this is an analog one. We've got our Raspberry Pi Pico, and there's this board which I just designed, and I've just got these plugs directly into the Raspberry Pi Pico. And just at the end, just here, this is my target, and this is the ruler for how far the target is from the sensor. So that's the setup that I've got for us. So I'm going to attempt to change screen to a different one. So if I remember how to do this, I think if I just stop sharing that for a sec, and then if I run them PowerPoints, and then forgive me everybody, I think where are you all? Hang on, everybody. Just trying to make sure I get the right screen because it's PowerPoint, and I've got a split screen here. It sometimes does catch me out, and I end up sharing completely the wrong screen with you. So let's see if I put that there, and then if I play that, then close that. Right. Okay. I think I might be about there. So hopefully.
Just while you're doing that, could you just remind us what those sensors were, please?
Yes, in fact, I've got them actually, and I've got the data sheets for you, so you'll see them all in a moment. So there's two we've got to tinker with. They're both infrared proximity sensors, since that's today's subject for us. And one's a digital sensor, we'll see that in a moment, and one's an analog. So we've got two that we can play with. Right, I'm hoping that you are all looking at the right screen.
Yes.
And not looking at pictures of yourself. Not that there's anything wrong with that. Right, okay, so hopefully that's now changed for you. So everything I've got here that we'll have a look at over the next hour is all available to download. It's there already. So, you know, if you're wanting to take notes, you don't have to. It's all there. Skip along to Silicon Cortex and season 3, and you'll find session 5. And I think it's about 4 or 5 different files. So there's this presentation, and there is some software, and there are data sheets on the 2 sensors. So easy. Right, so we are going to be having a look at infrared sensing, is the name of today's game. So we've got 2 as we just mentioned, analog one and a digital one. And whilst I'll admit this data sheet does look a tiny bit sparse, that is about as much useful information as I got off the data sheets. So the analog one, you can wire directly to the Pico because it's no more than 3.3. And just to remind you, the Raspberry Pi Pico, unlike other microcontrollers, is not 5-volt tolerant at all. You will do a power no good. So just a word to the wise. And as you'll see, the distance says 10 to 80 centimeters. So we'll have a look at that in a little bit more detail. So I've done a bit of work on that. And the digital one has got a much further range, but it's got different limitations. So we'll dig into both of these. So asking me just a moment ago about what sensor we've got here. So I've got these both sensors from Farnell. So if you wanted to scribble down the order code there, 3517933, it's £14. It's got a long lead coming off the end of it. And if I might be able to put the laser pointer on here, this might work. This would be very exciting if it works. Laser pointer. Right, you've got a laser pointer on your screen, I hope. So with the digital one, there is an LED on the back, whether you are within range or not. And to set the range with these digital ones, pointing at here, hopefully you can see that with my pointer. It's a screw, so you adjust this screw depending on the range. So you put your target where you want it, and then you'd adjust the screw until the light goes on or comes off, whichever way round it is. And yeah, they put these two sort of thumb wheels on, so you can just make a little housing for it. And I think the cable's about a meter or so, and it's just a 3-pin output with plus I think it'll run 3 to 7 volts, and the other one's just a digital output, which I think it's the output you'll find is probably like an open drain output. So it's always a good idea to make sure you've got a pull-up resistor. So it's dead easy to use this one. You set the threshold, and when you're within the threshold, and we'll have a play with these, I've got it all set up here for us. It'll just be 1 or 0. It really couldn't be easier. And then the other one, sensor, would be nice if that did change. There we go, and that works. So the analog one, I always think C looks like a typo to me. Similar price, £16. This has got an analog output, and as we saw a couple of slides ago, the maximum output's about 2.4 volts. In fact, most of the stuff I've got for us to have a look at is based around the analog sensor, because you can do a lot more with it, and it's a lot more interesting. However, as ever, it's not all peaches and cream, because this is the output from the analog sensor. And there's a few things. We'll have a look at how we deal with these. It says in the data sheet 10 to 80 centimeters. You can actually go a bit closer to about 6 centimeters, but then you suddenly have this problem, this roll off here. So as you get closer, for some reason it'll start to think you're getting further away from it. So that's why they've put this range of don't go less than 10 centimeters. Yeah, it'll still work to a point. So how to deal with that problem, we'll have a look at shortly. And obviously there's also this very non-straight line. And they also say, and we'll test this, I've got an experiment for us, whether you've got white card or I've got a bit of black card. Well, their claim is that you won't see any significant difference in the distance. So we'll have a look at that in just a moment, shall we? Right, click. There we go. So let's hop away from that now, and let's then just swap to the bench, and we can have a play. And I've got some MicroPython code, and we can have a look at them all. So, any questions so far, people? Good, right. Simples. We like simple. Right, so let me have a go now at sharing a different screen here. Right. So, so you saw the set. Let's just remind ourselves of this setup here, shall we? What we're going to do, and then we can have the code on the screen. So, right. So, just to remind us. Oh, let's turn that exposure up, shall we? There we go. Right. So, what we're going to do is you have to remember this bit. So, this is our digital sensor. And I've set that to just a distance, and we'll see that on the computer in a second. This is our analog sensor just here. These are just connected to our Raspberry Pi, which we'll have a look at in code. And then this is the target. So I've got a black target, which is here. And I've got a white piece of card. And after last week's small issue, I was talking with Ruth, I don't think it's on our call today. We were discussing, she was saying, well, what happens if you put a bit of carbon in there? Would a bit of carbon affect the readings? So this morning, I accidentally on purpose burnt my toast. So this is an awful lot of carbon in this, I reckon. So the question is, and I don't know the answer to this yet either, does carbon absorb the infrared and stop it measuring correctly? So if we'd been on the call last week, I guarantee we wouldn't be having that particular experiment. So we can always thank those good people who ruined it for us. Right, so I'll tell you what, let me just stop sharing that one. And if I can share a different screen on my computer, we can hopefully, is it this one? I think it's this one. Right, okay, let's explode that. Right, hopefully you can see our program. So what we're just going to have a little look at is just see how it works, what's working. And after that, we'll I'll grab a glass of water for a small commercial break. And then we'll have a look in a little bit more detail of the code and also some of the maths behind it, which I think is very interesting. So the Dig PIR is going to be my digital one. That's the yellow one, and that's going to be on 14. And the analog is actually going to be on 26. Yep. So let's make sure I've got all those in here correctly. So just very quickly here in our code here. So we're just going to read to digital. We're going to just, depending on what it is, we'll just send it back. And then we've obviously just going to read our analog one, and then we're just going to send that to the screen as well. Easy. Right. So it's not this one here actually. I'm going to show you a problem in just a moment that I've discovered. So if we run this program, just get it going. Right. So if you remember, we had our target. So our black target is now about a centimeter, about a foot away, and it's reading about 30 centimeters on the analog one, and it's now staring at the white one, and it's still reading 30 centimeters. So being black or white doesn't actually affect it, which is good. Right, now for the burnt toast. So I'm going to hold the burnt toast. I'm going to hold it on the good side. That's not burnt. It's at about 15 centimeters. Well, there we go. That's pretty spot on. So if we now point the bit of burnt toast, still 15 centimeters. And there you go. Look, so burnt toast does not affect the infrared reading. So if Ruth was on our call, she would now have the answer to the question that she posed to me last Wednesday evening on the phone. So if you think you're going to use infrared as a burnt toast detector, the answer is no, you can't. So what we can also do, the digital one, in fact, if I move this camera here, everybody, if I move this camera just there, maybe, should have thought about this, shouldn't I? There we go. Right. So yeah, so you can now see all that, can't you? I'm holding it. So this is the burnt toast. It's a picture of me. So just to reiterate, so there we go. So burnt toast still 15. Not burnt toast, still about 15. So there we go. There is the answer to Ruth's question. And with the digital one, if you put your hands in front, there you go. I've got a 1, and if I take it away, I've got a 0, and that is set with the screw on the back. One thing I will show you now is I discovered whilst writing all of this another bug in MicroPython. So this had me foxed for a little while. I'm going to put the camera back just so I can see you all. So I spent about a day trying to fix this problem. I couldn't work out what it was. So in my first bit of test program, so I've got 2 here. This is number 0. Originally, just to see if the thing was working in my code, here it is. This is my eternal loop. Yeah, where I'm actually reading what my sensor is, which is just going to the function digital PIR, which I've got just up here. And all I'm doing is I'm just reading the value. And if it's 0, I'll set proximity to 0. Otherwise, I'll call it 1. That's all that code is doing. And then it's returning the number, the result in proximity. So nothing complicated. And then I'm just printing it to the screen. Now, here's the bug I have discovered. So if I don't have a time delay in there at all, so it's just going to go around and round and round as fast as it can. And hopefully this will exhibit showing not working properly. So it's saying 0. Now, if I put my hand in front, the LED on the back's gone high, but the sensor, I think I'll show you again, look. Oopsie. Hang on, there we go. So there you go. Can you see the LED on the sensor? Is it changing on the screen? No. However, if I just stop the code and I put a small delay in there, and then I run it, it now works perfectly. Has anyone got an explanation for that?
No, I've seen it as well, but no explanation.
So I've come across this as well with CircuitPython, which is another layer on top of MicroPython. And I think it's when the events aren't using interrupts. And so under the hood, the Python interpreter is running a thread which checks the sensor. And if you have a tight loop with no breathing space, then it never releases kind of processing cycles to the other thread to check the sensor value. And so you're essentially reading the last value when you went into the loop indefinitely.
Huh, there you go. See, so it's not like a Stack Overflow error at all.
I don't. Well, that's my assumption rather than based on any evidence. But I've encountered this in MicroPython programs with quite a bit of kind of hardware, like LED driver boards and things, like LED matrix boards, where if you don't put a very short, it doesn't have to be 0.1. You can have a kind of 0.
Yeah, in fact, I think I found the sweet spot. I mean, I think I even tried, what's that? That's 10 milliseconds. Yeah, I played around with this to try and find the at what point did it work or not work. So that still worked. That obviously, I mean, even 10 milliseconds is an absolute eternity, isn't it?
Yeah,
Really?
so I think all it needs is enough time for the MicroPython engine to execute other instructions in the background.
Yeah. I mean, this one, what if I just, oh, crikey. So I've just set it to, well, 0.001, that's 1 millisecond. I'm pretty sure this had a bad hair day. Yeah, see, look, there you go. So look, so 1 millisecond, that's not very short, is it really? And you can see, look, the LED's going. So this had me foxed for some time. I was trying to work out, well, why isn't it working? I was going around in circles, and I even had a look. I thought, well, maybe is it a current drive problem? So look, so and it turned out to be a bit of a bum steer. I even put, I mean, it's in there now, like a buffer in, because I thought, well, maybe it's me. So this is just a not buffer, and yeah, and that didn't work. And obviously, I tried like a MOSFET buffer, and I concluded from that it had to be a problem inside the chip. Did you just say that you've seen this in CircuitPython, or
Yeah,
did I
which
make
is
that up?
yeah. So CircuitPython is just another layer on top of MicroPython.
Oh, really?
So it's running MicroPython under CircuitPython.
Fascinating. So let me just summarize before we have a 2-minute break where we can recharge our brains and grab a glass of milk and biscuits. On issues, I've now got about 4 issues I've found with the Raspberry Pi MicroPython. First one I found was there is a hardware problem where even 3.4 volts causes the Raspberry Pi Pico to hang. Because I was using the GSM module, and in fact, it's this one here actually. Look at that. What are the chances? So yeah, so this is the GSM module. Only starts working at 3.4 volts for some reason, and that 0.1 of a volt back powered to the GPIO on the Raspberry Pi and caused it to hang. Who would have thought? Obviously, I've also found that there's a issue with the SPI in MicroPython, where we'll do some SPI next month. But if you're using just the bytes, if you're just using the array command, then whenever you send a byte over SPI, which has got the 8-bit set to 1, it sends a random preamble byte, which completely had me. We have to use byte array, it doesn't happen. So that there's something a bit messed up in the SPI in MicroPython. Then there was this problem we found, and there was a 4th problem, which I can't remember for the moment, but it'll come back to me. But yeah, there's a 4th problem I found as well. So, you know what, you can get around these. Once you know they exist, you can work around them all. But it's just knowing that they exist, of course. You know, and as I find them, as I do these shows for us, I'll share them all with you, of course. Right, okay, so look, I'm just going to have a quick commercial break, glass of water, catch my breath, and do the same. Just have a minute, just recharge the brain, and then we'll have a little bit more look at the code. And I've then got an Excel spreadsheet which will explain a little bit more about when you've got these nonlinear sensors like proximity, how do you get an accurate measurement out of it? Because it's not as straightforward as you might think. So with that, I will share back to that. Okay, oops, days. And just say, if you want to make a note, if you haven't already, of the slides, you can. And just have a 2-second break. Catch your breath, I'll catch my breath. And I'll see you in just a minute. Right, I am back. So, quick swig of water. When you end up talking for so long, I need to catch my breath. Right, okay, so let's carry on. Hopefully you can all grab a glass of water. Well, wait. So we've had a look so far at just a couple of sensors, one digital, one analog. What I want to dig into now, which is going to be a little bit more faster paced, so try and stay with me, is let's just have a little bit more of a dig into how the software works and why we do what we do. So, as we're saying, we've connected the analog sensor to, in this case, it's pin 26, well, ADC 0, which is on GPIO 26. And the digital is on GPIO 14. Word to the wise is that while you think it's a pin number, it absolutely is not a pin number. It's a tiny bit confusing. Because as you can see, if we look here, top left, this is pin 1, but it's GPIO 0. This is pin 20. But it's GPIO 15. So in our code, it actually says pin, which is confusing. We are not referring to the pin number. We are referring to the GPIO reference instead. So that's just a little word to the wise. Right, now, the good news is we're now done with PowerPoint. So what we will do is, we'll swap to the MicroPython code and we'll have a little look into why we do what we do. And then I've got something else to share with you. So let's just hop back to, hopefully, it is all working seamlessly. Right, so let's just go back to our code, MicroPython 1. And let's just remind ourselves what was going on before the break. So when I started it, it would measure a distance. And if I move my hand in front of the sensor, trust me, I am, then it measures a distance. Of course, if I get too close, it'll start to say, you are too close. We'll have a look at that in just a second, what's going on and why we do what we do. So with the analog one, what it's doing is, if I can find it here, there you go. When it goes to the analog, V is the voltage it's reading, and L is the distance from the sensor, or length is, there we go, length. And there's an equation here. So this equation is not linear, it's got scaling in it. So if you remember when we had that original graph which went up and then came down, that down curve is represented by this equation. Now in just a moment, we'll have a look into how you arrive at these numbers. So what I'm doing is I'm just reading it 100 times, and then I'm taking an average. That's all I'm doing. This is the code for reading here. It says 3.3 divided by 65535. 3.3 is the maximum voltage that you can read. And of course, there's 65,000 levels. So this is like a scaling factor in order to get to the correct voltage. And the voltage is then related directly to the distance from the sensor. And that's what all of this here, these are the parameters that go into this equation. So we'll have a look in just a moment. How did we arrive at all those funny numbers and why? So that's all the code this code is doing. So you can easily grab that code. It's all there to download. So, and then what I've done is, depending on what that distance is, I've then got some fuzzy logic. Fuzzy logic is just an if-then-else computer statement. And if you're using if-then-else statements to capture an analog event, my top tip is make sure the code covers every single eventuality that can happen, because you never know, there may be some events where you get a value that then cause it to do something a bit screwy. So if I didn't have these last two lines, and I only worried about the distances that are within the data sheet, well, what would happen if I suddenly measured greater than 80 or less than 8? So always make sure you've got that in. In this case, I'm just saying you're either too close or you're too far away. So just to prove that point. Okay, so that's 18. So if I come too close to the sensor, so my hand's right in front of it and you're saying you're too close, go away. But if you get really too close, then look, it starts to really mess up. It now thinks, although, I'll move my hand here, we'll have a look at this in the math, how we deal with this problem. I'm just trying to move the camera to the right place. Right, so as I move in front, okay, saying 10 centimeters, as I get less than 8, it'll then say you're too close. And if I start to get even closer, it'll start to say, I'm right on top, but now it's saying I'm now getting further away from it, but I'm not. So there is, with these analog sensors, an issue. So you need to find some way to deal with that problem. So the easiest way to do it is in the data sheet, it shows that you can actually measure to say, I think go to about 6 centimeters closest, but the data sheet says 10. So you've got that little bit of leeway to say you're getting too close, back off and go back to normal. So you'd have to find some way to manage the fact that you're about to crash into a wall, because it suddenly thinks you're not going to crash into a wall. It thinks you're actually going to. I've now got plenty of space, and I haven't. I've got about 1 centimeter. Whereas I think the logic sensor doesn't have that problem. Look, I'm right in front, and look, and it's okay. Where is it? Hang on, so let's go. Let's see it. There you go. 1. Oh no, the digital one does it as well. There you go. I've learned something new. So the digital sensor has exactly the same problem. Further away, the threshold which I set with that screw, if you remember. Yeah, okay, 1, and then if I get too close, it goes back to 0. So both these sensors have that problem if you get too close. So I guess what you've got to do is put a stick in front of it, haven't you? I don't know if ultrasonic distance would solve that problem, or whether that would have backscatter issues. I generally do not know.
I've tried it with ultrasonic sensors, and I've not seen that, Stevie.
Well, really close. When you get really close, it doesn't suddenly crap out on you.
No, it seems, roughly linear right the way through to touching.
How interesting.
Because the ultrasonics, you have a transmitter and a receiver unit, and they're spaced apart. I think when your target gets too close, you effectively block the ultrasonic from getting to the receiver.
Right. Oh, okay.
So you've essentially got the same problem as your digital one, but unless you're getting a reading, you don't know whether there's something really close or nothing.
Right. Okay. So it needs to have a feeler stick out there.
Yeah. With the ultrasonic, if you're not getting a reading back, you don't know if it's because the sensor's right up against something or whether there's nothing for it to bounce off. Yeah,
I imagine that if you're building like a robot, the way to probably, I suppose, I was thinking about this, but maybe you'd have to, if this pen's a sensor, of course, a mouse pen. If this is the robot, you'd probably, if you mounted the sensor further back, you might be a way to actually solve the problem. I don't know. But
yeah, having something that physically prevents targets getting closer than the minimum distance that works is a practical solution.
Yeah, yeah. So, right, let me swap because what I want to show you now, this is just the last little bit I've been working on, which might be a little bit heavier, but hopefully not too much, he says. So what I wanted to dig into now is how, this is just for the analog sensor, not for the digital, of how can I accurately measure the distance? Because that distance of measuring really is pretty accurate. So bear with this because this tells a story. And if any of this is not clear, please just stop me and say, huh? Say that again. So what we've got here to start with, hopefully this is sharing, it's an Excel spreadsheet for you, and this is all downloadable as well. Is this screen grab here, which I've just clicked on. I'm not sure if you can see my mouse. It is the actual from the data sheet for the sensor. So what I've done is I've replicated that in this graph by measuring these points on the different differences. And then I've done that with a ruler, and then I've just transposed it into an array, and then I've just plotted it. So that's how I've got that data in. So what I want to try and do, and I'll share with you, are it's actually 4 different ways in which you can use a non-linear sensor like ultrasonics, like infrared, to be able to do some accurate measurement. Even light sensors, like dependent resistors, are non-linear. Most sensors are non-linear. It's just the way of the world. So what I've done further, I've actually just in this graph here, just flipped it upside down because it's usually, certainly myself as an engineer and a scientist of 30 odd years, you normally have the variable you're controlling on one side, or measuring, I should say, on the x-axis, and then the result you normally put on the y-axis. So here, of course, if I'm going to be reading a voltage, and that voltage is then going to be an appropriate distance. It's exactly the same as this graph above. I've just flipped the x and the y-axis. I've also, just for the moment, and we'll come back to it when we get to the last 2 tabs here, I've just cut off and said, let's not worry about this 0 to, what is it, about sort of 6 centimeters. Let's just forget that for the moment, because it's just going to complicate the story. So what we want to have to come up with is, how did I arrive at that equation which I had that got the distance? So there's 3 key ways you can do it. One of them, and I've mentioned this on some previous sessions, is called linear regression. There's nothing new here. This is old school mathematics. I actually got this out of my book on statistics called Teach Yourself Statistics, and I got it from Heifers in the centre of Cambridge. And it's a formula, and how they arrive at the formula, we don't need to worry about. But in the formula, it's telling you to, well, the x value times the y value, and sum them, do the sum of the x times the sum of the y, and you get the idea. I don't know how they came up with this, but they did. Whenever I'm doing equations in Excel or in the computer, I do always split them up into components. Rather than trying to do all this one massive equation, I just always try and break it down. If I get an error, it's certainly easier to spot it. And there's also less chance of making an error. So with this magic formula, and let's say it is magic, you can work out m, and m is the gradient. And then c is where it cuts the axis. So y equals mx plus c, GCSE O-level maths. This is usually what we learn. And if it's got a bar over the top, that means it's the average or the mean. So those parameters I've worked out here, and they've come from the table up here, which I got from copying the data sheet. And if I do that, then it tells me what my gradient is and where I cut the axis. And then I've plotted it. So this is the computer's attempt at a best fit curve, a best fit line, sorry. The orange one is the best fit straight line for this curve using this well-known formula from a statistics book. Personally, I think it could have done a better job. I'm sure, like me, you probably think maybe it could have done slightly better. But I think the point here is wherever you put that straight line, it's always either going to be over-reading the distance or it's going to be under-reading the distance. In fact, it's only at 2 points is it ever really going to be accurate. So how good is that solution? Depends how linear or curved the data is. In the case here with the infrared sensor, it's clearly not great. So let's move on to something a little bit more sophisticated. And here it is. What if, rather than having a curve or straight line to try and fit the curve, we actually used a number of straight lines? And here I've used 3. So depending on what value I read from the ADC, will dictate which curve, which line I want to be on. And all I need to do is work out at what point do all these lines intersect. And where they intersect is where I decide to jump to the next curve. Hopefully that's all simple. We can all see that. If I just delete that, there you go. So you can see that one there. And I think if I delete that gray one, there you go. So they can see. So what I'll be doing, I'll just be using bits of a curve, bits of a straight line rather, to represent the curve. So it's certainly better than the straight line. But in terms of code, I've now got a little bit more complicated code. I've now got to decide in my code, well, what is the number? Depending on what range I'm in, I've now got to decide which curve I'm going to be, which straight line I'm going to be on to get my approximation. And that's called linear interpolation. So a slightly more sophisticated way, moving on from that, and this is how I've done it, is to use a non-linear representation. And this is how my approach is to machine learning. So I'm going to get around to talking about this eventually, or as I call it, machine intelligence. Machine learning is, there's a number of different ways of looking at it, there's a number of theories. One of them is called supervised learning, which is when you're trying to find, you've got some information in your data and you're trying to make a curve fit the data in order to use it as a prediction for the future. So the straight line idea would be just worse than terrible. So with our maths hats on, our raw data curve that we had from the beginning is actually a 1 over r curve, 1 over x, r being a distance, x being a distance. That's what I've got here. That's this curve here. And that doesn't look too far from our raw data. So what I need to do is find a way to maybe move this curve, which I've highlighted, up and down. So I could move it up to here or down to here, or move it left or move it right, or even move it up and across. So having a handle on what the equation is likely to be, we can then take a near representation of it and stretch it in the x-plane, which is across here, or stretch it in the y-plane and move it about and see if by moving it around, can we get something that sits in the right place? And I was quite lucky when I worked this out. It actually, luckily, worked almost first time. And this is my answer. So, and you can see, so one of these, I think it's this one. That's the raw, that's the original data. And using that previous equation of scaling, so I've multiplied, and it was just practicing until I've got one that fit, really. But you could just have a program to go around and just try and work it out until numbers match. So I scaled it by 33 and I just moved it down -4. Well, I actually moved it up. It was a negative number to move it down, which was a bit confusing. You can see here, in order to move the line up you add +1. To move it down, -1. To move it left, it's +1 on the end. And to move it right, it's -1. It's a shame that wasn't the other way around, but that's just the way it is. So with that, I've now got an equation that I can now put into the program. So the program I actually did have this equation, 33 times the ADC voltage, and I've subtracted 4.6, and that's how it managed to read so accurately. And by doing the work up front with this little bit of maths, the code becomes so much easier because I'm just running up and down this curve. Now, of course, we do have some limits, don't we? Because don't forget, we don't want to be going less than 6 centimeters, because then things start to go a bit wrong. So that's where I got to last week, and then I was going to say thank you very much. Because of last week's problem, it gave me the week to think about how could I solve this problem of here. Could I do something about that? So I've had the week to think about that, and this is my answer. So can I find an equation that fits both this line here? And it's quite straightforward to do. You could either use linear interpolation, linear regression, which we saw at the beginning, or another way of doing it. If we know it definitely is a straight line, we could just take 2 points. If we just had 2 points, we could easily work it out. And this is the formula. I worked it out, that if you had 2 points on a known straight line, and you wanted to know the middle one, this is the formula, which would actually give it to you. So it's quite easy to derive. I've actually got it in my notebook, but I won't go through the derivation. Trust me, it's true and it works. But you can only use this sort of formula if you know this is an absolute straight line, which is what I've got here. If it wasn't a straight line, then of course you'd have to do something like this and use a slightly more complicated formula. So swings and roundabouts. And then finally, what I've called multi-polynomial regression, a phrase I made up, is let's put the two together. So is it the gray line? No, the blue line is our original graph. Oh, there you go. The blue line is the original data. Let's get rid of that. You can see it all. There we go. So underneath this orange line is actually the rest of the blue. If I cross that with that, you see it? There it is. Yeah, so that's our original data, the blue one. I just do that. So what we want to do, remember I was saying about that linear interpolation of jumping between two curves? That is what you'd have to do here. So we've got one curve here, and then we've got another curve here, another straight line here, and the intersection of them we can actually work out mathematically. And the way I've done that is it's just algebra, quadratic equations. So I know what the equation is for the straight line, and I know what the equation is for my nonlinear component. And if I just equate the two, because they'll both be meeting at the same points on the y-axis, which is turns out to be about 3.2 centimeters. So the point at which they perfectly meet, I can very easily just rearrange this equation and work out what the voltage will be. And it'll either be 3.2 volts or minus 5.75. Where do you get minus 5.75 from? Of course, if you were to plot this graph for this curve, if you were to go negative, you'd actually see this reflected and upside down. But of course, we can't go negative, so minus 5.75 is not actually valid for us. It's an answer to the equation, but it's not something we would use. So how to get from this curve to this curve, I'm going to leave that as a teaser, because next time we're going to be looking at co-processors using the Raspberry Pi. And I will work out, not done it yet, I'll work out how we jump from one curve to the next curve in real time without affecting any other performance parameters. And that's a good use of using a math coprocessor, or I call it anyway. So that's me rabbiting on. Any questions, any thoughts?
It's just is reminiscent of calibrating thermistors on 3D printers.
Oh, really?
Where you've got exactly the same problem of they return a voltage and you have to map that to a temperature. And all the different brands of thermistors have different profiles. And the way the firmware actually gets you to input the data is as a CSV file.
Mm-hmm.
So it's probably doing some of this maths under the hood in the firmware. This is Marlin firmware that I was playing with.
Yeah.
But actually kind of getting the profile in the first place, when you've got an unknown thermistor, requires lots of careful measuring of real temperature versus what it outputs to the printer.
Yeah, you know, on that very note, when I started looking at working with with machine learning, I had this theory that, well, if I could have a generic equation, a polynomial, where if I could have it, you know, ax to the a plus b x to the b plus c x to the c, or small c and big C, of course, for coefficients. Could I have a polynomial like that I could use as a generic equation, and then the data would then sort of work out whether, like, you know, x cubed was a part of it or not? And the answer is absolutely no, you can't. I was told it's a great idea, but it'll never work, and they were right. So the way I approached it, and I approach it now, is you need to have a rough idea of what the curve equation is going to be. For example, just to go back to here, whichever one it was, is it this one here? Yeah. So with our raw data, I know that is probably a 1 over x function. I've done a maths for enough years to know what it might look like. You know, it's clearly not a sine wave. So it's knowing what is the best curve for it, and then, as I say, just moving that curve around with the maths to try and make it fit, and then you've got a good equation.
Yeah, I really like the approach you've outlined here. Of course, it sidesteps the real problem that now you've got two essentially equations for your two lines. It means from your sensor, all your code can really tell is that there are two possible distance values for any reading.
Yes, absolutely right. And so what I've been thinking about how to deal with that problem. Let's go back to here. I've been thinking the way to deal with that, and again, this is another good, this then feeds into, this is a teaser for next time. I'm thinking maybe the way to deal with that is, if you know in which direction you're going, then that will give you an indication as to which line you're on. Because if I let's say I was moving at a distance, I know, so I'm going to 1 meter per second or something, or maybe not 1 meter per second. Let's say 1 centimeter per second, or 10 centimeters, because this goes up in 10. So there you go. I should have thought about that. So if I knew 1 second I was there, and the next second, and if I knew 1 second I was at that point there, hopefully on your screen, and the next time I was at that point here, that's showing up on the screen, of at 20, I would know that the gradient between the two is negative. In which case, I know that I'm actually on a downward slope, and I'm heading towards this what do you call it, an apex. the inflection point, whatever you want to call it. So if I know in which direction I'm moving on the curve, then I'll know which line I'm on. How well that would work, I don't rightly know yet. It's a thought. I don't know if anyone else has got any opinion on whether that theory would work.
That would work if you could make the assumption that there was nothing moving in your scenery. So if your robot was the only moving object. But if you're dealing with other obstacles that may move independently, of course, all bets are off again.
All bets are off. Yeah. Or I was wondering, what if you had two sensors, offset from each other? Would that work? So
yeah. So I was about to say, sensor fusion is kind of the solution here. Another great example of this problem is GPS positioning, where if you've kind of got a fix on one satellite, you know where you are on a sphere around that satellite.
Yeah.
If you've got two satellites, then you know where you are on two spheres, which means you're somewhere on the circle of intersection of those two spheres. If you had a third sphere, then now you've got two circles, which means there's 2 points where they intersect.
Mm-hmm.
So by adding more data from essentially more readings, you narrow down the possibilities, and you have to have enough readings to be able to eliminate all the possibilities.
Okay, there we go. Yes. So nothing's ever straightforward, is it?
No, these problems, real world problems, are often much more complicated than the electronics design that's giving you the data.
Yeah, and of course, when you go and buy sensors, these real world problems they're never part of the sales package that you actually buy, which is another pet subject that I won't get onto right now about the state of education in this regard. So anyway,
just one other point, that the big problem with proximity sensors that you also need to account for is that sometimes you get readings from more than one target. And so in your noise, you might actually be chopping between two possible distance values. And if you just take an average, then you effectively measure a distance in the middle of the two real measurements, rather than, so you have to look at clustering of your readings as well as
I'll tell you what, why don't we try that right now before we all go and put the kettle on. Let's run the program, and let's do exactly what you've just said and see. Right, hopefully that's sharing the program with you all.
Yeah,
fantastic. Right, let's try what you just said. So let's put I've put a watch. In fact, let me move the camera so you can see. It'd be nice to have a split camera on this. I'd love to work that out, but right, okay, but we've got desk cam. Right, so I put my watch in here. There you go. So it's measuring my watch at well, that's interesting, isn't it? Right, so let's try let's try something different. Hang on. Oh, here's a box. Right, okay, so we've got a box here. There we go. So there's a box, and that's about 10 centimeters. Right. He says, picking up, there you go, the target shield. Yeah, so look, right, yeah, so 45. So yeah, so look, so it's really getting upset, isn't it? So it's got two things in its field of view.
Yeah.
So you're absolutely right. There you go.
So if you actually looked at your 100 readings in your averaging loop, you might find that you're getting two kind of clusters of values. But you'll also have noise as well. And so it actually becomes quite a complex problem.
It does, doesn't it?
It's particularly problematic with the ultrasonic ones because they have quite a wide beam. They reflect off a lot of things. And so in a real world, like trying to drive a robot under a kitchen table where you've got chair legs and table legs.
Yeah.
Trying to make sense of that data is a real challenge.
Fascinating, isn't it, really? Yeah. What do you think might be a rather small topic? Suddenly can get very complicated, can't it?
Yeah.
There we go.
Stephen, the only other thing I was going to add is I used the Chat GPT chatbot, AI chatbot, to suggest some code using the sensor ID you gave us, the GY2YO, etc. And it came up with some suggested MicroPython code, including an equation for working out at least the downward sloping right-hand part of the graph. So kind of a cheaty way of doing it, but I think it might be interesting, so you don't have to go through the whole regression calculations in order to come up with a formula.
Right. Okay, right. Look, it's 8:30, just gone, and I'll just show you something. So next time on How to Design Electronics, we're going to look at math using a Raspberry Pi Pico as a co-processor. So I've done it some time ago here, and it's not straightforward as what you think. You can't just small teaser. You can't just stick it on the back of your Raspberry Pi Pico and think it off. It's a tiny bit more complicated than that. So we'll have a look at that, and we'll build. I'll hopefully have a bit of time. I've only got 3 weeks to see if I can build upon some of the discussions we've had here and use those and implement them into the like a co-processor idea. So yeah, so come for part 2, I suppose is what I'm saying. So with all of that, if all of this is available to download, I've put this on my Silicon Cortex site. The spreadsheet's there in its entirety. The code is there, and the few slides there, and also the data sheets I've put on there. The data sheets are pretty rubbish, I tell you, for these 2 sensors. So with all that in mind, I will say thank you for joining, and we didn't have any interruptions, so I didn't have to kick anyone off, but I've now got that power for the future. So I'm supposed to say thank you, and I'll see you next time.
Thank you. It's been great as usual.
Thank you very much.
Thank you very much.
Thank
Brilliant.
you. Bye.
Bye. See you all next time.
Bye.